Hi all, I am Nidhu Nessus. Today we are going to deal about Kepler's laws of planetary motion. Without further delay, we can start the class. Here you can see two models. One is the geocentric model and the other one is the heliocentric model. Geocentric means geo means earth and centric means center, and this theory was proposed by Ptolemy. According to him, Earth was the center of the solar system and the center of the entire universe, and all planets, including the sun, revolved around it. And this is the heliocentric model. According to Copernicus, sun was the center of the solar system, and all other bodies revolved around it. So here you can see the timeline. Before Copernicus it was Ptolemy, after him came Tycho. Tycho is an important one to note as during his time no telescope was available, even though he collected a huge amount of data using his naked eye observations and using instruments like sextant. And after him came Galileo and Kepler. Galileo was the one who invented the telescope, and after them, and the Kepler joined Tycho as an assistant at the age of 27. Tycho gave an assignment to Kepler to define the orbit of Mars. Kepler carefully studied his data and proposed two laws in 1609 and one more law in 1619, and these three laws are together known as the Kepler's laws of planetary motion. After them came Newton, and we know his famous laws of motion. Some of the Kepler's laws can be proved using Newton's law. This you can read later. This one is important, and these are the statements proposed by Copernicus. First one is that the planetary orbit is a circle with epicycles. The sun is approximately at the center of the orbit. The speed of the planet in the main orbit is constant. Even though Copernicus was right by saying that sun was the center of the solar system, there were some mistakes in his statements which were corrected by Kepler. Here is the first law, the law of orbits. According to this law, all planets in our solar system orbit the sun in an elliptical shape with sun at one of its focus. So here we have representation of a circle and an ellipse. If we look at this circle, it has a fixed point called center, and its eccentricity will be equal to 0. All the points in the circumference will be equidistant from the center, and this constant distance is called the radius. If we look at ellipse, there are two fixed points which are known as the focus. One is here and the other one will be here, and sun will be one of its focus, and the planets like this blue dot will be revolving around this elliptical path. Here is a detailed picture. So this is an ellipse. BC represents the minor axis and PA represents the major axis. The distance from B to this center point can be called as B, which is the semi-minor axis, and the total length will be 2B, which is the length of the minor axis. This P to this point will be A, so the total length will be 2A, which represents the length of the major axis. Here we have two focus, that is S and S dash, and sun is at S, one of this focus. What are the peculiarities of these points P and A? Here P represents perihelion and A represents aphelion. Peri means near and aphelion represents a farther point from the sun. So when a planet revolves around the sun and it reaches P, it will be least distant from the sun. And when a planet reaches A, it will be very much farther away from the sun. So PS is least distance and SA is a larger distance. According to Newton's gravitation law, we know that F is inversely proportional to the square of the distance. Since PS is a smaller quantity, the square will be also less, and the overall force acting here will be larger. So the velocity of the orbiting body will be very much high in perihelion, and when it reaches the aphelion point, that is A, the velocity will be much lesser since force acting here will be less. This can be also explained by F is equal to ma, as F is directly proportional to A. When force increases, the acceleration of the planet also increases. So here at P, force will be larger, hence the velocity will be larger. At A, force will be less, so the velocity will be less. Here are some implications of the first law. First one is that the law states that the planetary orbits are not perfect circles but ellipse. We have discussed this, and the closest point to the sun in the orbit is called perihelion and the farthest point is aphelion. This also we have discussed. Elliptical orbits means that the distance between a planet and the sun changes over time. Since it is not a perfect circle, the distance between the planet and the sun will be changing every time. The second law, which is the law of areas. A line drawn from the center of the sun to the center of an orbiting body will sweep out equal areas in equal intervals of time. We know that a planet is revolving in an elliptical path, and at this point, when it travels from T1 to T2, it covers an area of A2. And when it reaches here also, T1 to T2, the area is A1. And we have drawn a line from the center of the sun to the center of the revolving body, which may be a planet, comet, asteroid, etc. So when this is a position vector, the line is known as position vector, and the position vector is sweeping areas A1 and A2. If we take a time interval, same time interval delta t, which may be of 1 month, 2 months, etc. In same time interval, we can observe that these two areas sweep out will be same, that is A1 will be equal to A2. And the second law is also based on the conservation of angular momentum. We know that no external torque is acting on the revolving body, so the angular momentum is conserved here. Yeah, the first one, the implications. This law implies that a planet moves faster when it is closer to the sun and slower when it is farther from the sun. This we have explained in the first law. It reflects the conservation of angular momentum for the planet-sun system, as no external torque acts on the planet. The third law, which is the law of periods, also known as the law of harmonics. According to this law, the square of the orbital period t of a planet is directly proportional to the cube of the semi-major axis of its orbit. We know that time period t is the time taken to complete one revolution around the sun, and I have defined what is a semi-major axis using A. So t square will be directly proportional to a cube. In order to remove proportionality, we have added a constant called k. So t square by a cube will be a constant. Let us see what does this law implies. First one, this law shows that the planets farther from the sun take longer to complete an orbit than those closer to the sun. We know that the inner planets, which include Mercury, Venus, Earth, and Mars, take less time period than the gas giants, which are Jupiter, Saturn, also Uranus and Neptune, which have longer revolution period. And this can be explained using Kepler's third law, that is, since for outer planets this A will be larger, the time period t also will be larger. The constant in this relationship depends on the mass of the sun and is same for all planets orbiting the sun. So we can see here a constant called k, which have got a specific value, and this depends on the mass of the sun. And since we know that mass can neither be created nor be destroyed, the sun's mass remains a constant, and so the the k will be same for all planets from Mercury to Saturn, Uranus, Neptune, etc. I hope you have understood the topic. Thank you for hearing me. We will be seeing in the next section. Thank you all.